Have you ever wondered what's really going on inside the mind of an AI? You know, it can feel like some kind of magic, but behind every single decision, every image it recognizes, there's a secret language at work. And that language, it isn't some futuristic code, it's math. So today, we're going to pull back the curtain and translate it. So let's start with a really big question. How do we teach a machine to do something we humans do without even thinking about it, like just seeing and understanding the world? How does it learn to tell the difference between a face, a car, or a cat in a photo? Well, here's the trick. We have to translate our complex, kind of messy world into a language that a machine can actually process. We need to convert sights, sounds, and even our ideas into its native tongue. And that language, the absolute foundation of all modern AI, is mathematics. But hey, don't worry, it's way more intuitive than you might think. All right, so how do we even begin to translate reality into numbers? Well, we start with the absolute building blocks. The field of linear algebra gives us the basic vocabulary. You can think of them as the nouns and verbs to describe data in a way a computer can finally get a handle on. Okay, take a look at this incredible image of Stonehenge. To our eyes, it's, ancient stones, grass, a dramatic sky. But to a computer, it's just numbers. A giant grid where every single number represents the brightness of one tiny pixel on a scale from pure black to pure white. And this grid of numbers, that is our first key concept. So this grid, it's got a formal name, a matrix. It's really just a neat rectangular block of numbers. And in the world of machine learning, matrices are, well, they're everything. They are the fundamental containers that hold our data. An image is a matrix, your movie ratings on Netflix can be a matrix, even the words in this sentence can be turned into one. They are truly the nouns of AI's language. Okay, so we've got our data all packed up neatly inside a matrix. But here's the thing. A single image matrix can have millions of numbers in it. That's a lot to process. So the real magic isn't just about storing the data. It's about finding the essence of it. And that's where this really powerful idea called matrix decomposition comes into play. I mean, think about it for a second. Do we really need every single one of those millions of pixel values to know that we're looking at Stonehenge? Or is there a simpler, more compressed way to capture its core idea? This is one of the biggest challenges in AI, how to deal with these massive amounts of data efficiently. And this quote really hits the nail on the head. We're not just trying to make the file smaller, like zipping a folder. We're looking for the hidden structure inside the data. We're trying to filter out all the noise so we can find the meaningful signal underneath. One of the coolest tools for this is called singular value decomposition, or just SVD for short. Think of it like a prism for data. You shine the image through it, and it splits it into its core ingredients, a set of basic patterns all ranked from most important to least important. So what happens if we try to rebuild the image using only the single most important pattern? Well, you get this. It's blurry, it's abstract, but you can kind of make out some vertical and horizontal shapes. Now, let's just add the second most important pattern into the mix. Okay, things are getting a little clearer now, right? You can actually start to make out the distinct shapes of those giant stones. The essence of the image is slowly coming into focus. But now, look what happens when we jump from just 2 patterns to 20. Wow, it's pretty incredible. With just a tiny, tiny fraction of the original data, the image is now unmistakable. That's Stonehenge. We've basically captured the soul of the image with just a sliver of the original complexity. And that is the whole point. This is the core of intelligent compression. SVD lets an AI focus on what matters most, the patterns that carry the most information, and just ignore all the fine-grained, less critical details. It's the mathematical version of seeing the forest for the trees. So, representing and compressing data, that's one piece of the puzzle. But how does an AI model actually learn? How does it get better at a task over time? For that, we need to add 2 more tools to our mathematical toolkit: calculus and optimization. This really gets to the heart of what we mean by machine learning. A model usually starts out just making random guesses. So how does it have any clue if its guesses are getting better or worse? Whether it's trying to identify Stonehenge or predict the stock market, it absolutely needs a way to measure its own performance so it can improve. The answer is actually a surprisingly elegant idea. The model calculates something called an error or loss score. It's just a number that's really high when its predictions are terrible and gets lower and lower as they get better. The entire goal of learning, then, is to just keep tweaking its own internal settings to make that error score as small as humanly or machinely possible. The best way to picture this is to imagine you're standing on a foggy hillside, and your only goal is to find the very bottom of the valley. This whole process is called gradient descent. So at every point, you check your elevation. That's your error score. Then, and this is the cool part, you use calculus to figure out the steepest direction down from where you are. This direction has a technical name, the negative gradient, but you can just think of it as a compass that's always pointing straight downhill. You take one small step in that direction, and then you just do it again, and again, and again. You repeat this whole process until you can't go any lower. That lowest point is the best possible version of your model. So calculus gives you the compass, and optimization is the journey of walking down the hill. Okay, so we've got data structures, a way to find patterns, and a method for learning from mistakes. But there's one last critical piece. The real world is, well, it's messy, it's unpredictable, and AI needs a way to deal with all that uncertainty. And that's where our final tool comes in, probability. Probability theory is basically the mathematics of maybe. It gives our AI models a way to reason about things that aren't just simple black and white. So instead of making a single definite prediction, a model built with probability can tell us how confident it is in all the different possible answers. And this is such a huge deal. It's the difference between a model saying, the answer is 5, and a model saying, I'm 95% sure the answer is 5. Or I'm 98% sure that's a cat, but there's a 1.5% chance it's a small dog, and 0.5% chance it's a loaf of bread. This kind of nuance is absolutely essential for building AI systems that we can actually trust, systems that understand the limits of their own knowledge. So there we have it. We've touched on 4 pretty distinct fields of mathematics. Now let's just take a step back and see how they all snap together to create this complete toolkit for building intelligent machines. It really is a beautiful system when you see it all together. Linear algebra gives us the nouns, the matrices to hold our data. SVD and other decompositions act like verbs, helping us find hidden structure and simplify that data. Calculus is our compass, always telling us which way to go to get better. Optimization is the engine, actually driving that learning process forward, step by step. And finally, probability gives the model a sense of wisdom, letting it handle uncertainty and express confidence. Every single part is essential, and together, they form this unbelievably powerful toolkit. And that's it. That's the secret language of AI. It's not magic, it's just a powerful conversation happening in the language of mathematics. And now that you have a little glimpse into how that language works, the final question isn't just about what machines can do, it's about what new, creative, and world-changing problems you would teach them to solve.